Our next speaker is, oh, you are good and evil are very, Benedikt Ahrens, who will speak about the Univalence Principle.
Thank you very much. Yes, so I would like to discuss this talk, the formalization of category theory in univalent foundations. As a brief introduction to this topic, what is univalent foundations? Well, I will explain this in more detail in just a second, but for the time being, it's sufficient to know that it's a foundation of mathematics developed by Vladimir Blavatsky and other people in the past 20 years almost now. What do I mean by formalization? By formalization, I mean the formulation of reasoning in a precise and possibly machine-checkable format. So one of the motivations, for me, my motivation is to have machine-checked proofs. I'm using computer proof assistance. This talk is not about computer proof assistance, but obviously when you want to explain something or have something checked by your computer, then you really have to formulate your reasoning in a very precise and machine-checkable format. You all know what category theory is, and the goal of my talk is to show how univalent foundations can serve as a suitable, as a convenient foundation for the formalization of category theory. This is the summary of the talk, and maybe if you just remember one thing of my talk, it's shortly the slide maybe. Sameness is a fundamental concept in mathematics. And set theory has a flaw, which is that the notion of sameness that is provided by set theory, by set theoretic equality, is often not the sameness that we're interested in. Category theory is, one purpose of category theory is in particular to provide a correct and mathematical notion of sameness that is more useful in the form of, well, in the form of isomorphism, in the form of one category theory, but also, of course, in the form of equivalence when we go out and so on. And in contrast to set theory, univalent foundations allows one to express reasoning exactly modulo that kind of sameness that category theory provides us with. So, in short, in set theory, we have the foundational and the mathematical notion of sameness that diverge, and in univalent foundations, they coincide. And this related to the notion of good versus evil. There's good category theory, where we consider objects up to isomorphism, and then the right notion, the notion that results of sameness for categories is the notion of equivalence of categories. And there's evil category theory, where we consider objects up to equality, and then the correct notion of sameness between categories is the notion of isomorphism of categories. And it's an obvious question, how to know good from evil? How can we distinguish between those two? There were some other people who have thought about this in the 70s. Georges Blanc and Peter Fried developed languages, first-order logics, essentially, that are invariant under equivalence of categories. And the main way to achieve this is to disallow talking about equality of objects. And Mackay's false first-order logic with dependent sorts tries to go beyond that by not talking just about one categories, but also about higher categorical constructions. And this first-order logic with dependent sorts is supposed to be a language, and is a language where one can only make statements that are suitably invariant under the correct notion of sameness, the good notion of sameness. So Mackay also coins this principle of isomorphism, about which he says that it's the character of this principle is that of a constraint on the language of abstract mathematics. Welcome one, since it provides for the separation of sense from nonsense. And so good versus evil, sense versus nonsense. And very much inspired by this work by Mackay was Vladimir Blavatsky, who then developed the Univalent foundations with the purpose of also having an invariant language. but not just a logic that allows to talk about statements, but also as a real foundation of mathematics, that is, where one can also do constructions. And also these constructions that one does on mathematical objects should be transported suitably across equivalence of objects, where equivalence of objects depends, of course, on the notion, on the objects under consideration. And it didn't take very long to prove that Blavatsky's dream of an invariant foundation was indeed the case for particular classes of mathematical structures. So, for instance, Cocon and Danielson proved what I call a univalence principle in univalent foundations. And this is here stated very sloppily. What I mean by it is that whenever you have a construction on groups, which are called P, a construction P on groups, and two isomorphic groups in univalent foundations, then this construction carries across their isomorphism. Yeah. So in other words, in univalent foundations, it's impossible to state something that is not invariant under, to state a property of groups or a construction of groups that is not invariant under isomorphism of groups. And also for categories, one can have a similar result, which I will explain in a bit more detail in the next part, where whenever we have two categories, A and B, then they have all the same properties that one can state in univalent foundations. So, in other words, in univalent foundations, it is impossible to do evil category theory. That's not exactly true, but it's true for this kind of category. Actually, there will be two kinds of categories in univalent foundations. A kind of category for evil category theory and a kind of category theory for good category theory. In my talk, I want to explain how we generalize these results, subsume them by a theory of mathematical structures and univalence property or a univalence principle for mathematical structures specified by that theory. So we have a notion of theory that I will present to you. And instances of these either categories or groups or other things. And we will have a similar result for the models of that theory. Okay. Feel free to interrupt me at any time. I will now give a brief description of univalent foundations, then explain the univalence principle for categories in a bit more detail, and then give a very short overview of our work on generalizing that to other mathematical structures. So, what are univalent foundations? The primitive objects of univalent foundations are not sets, but they are infinity groupoids, also called types or spaces. I will use all these three words synonymously. So A and B, for instance, here are types or infinity groupoids, and the objects of an infinity groupoid, we denote them like this here. X, column A means A is an infinity, is a type of infinity groupoid, and X is an object in that thing, and Y is an object in B. And then we have a notation for higher cells that is shown here. So here F and F prime are one cells from X to X prime in the groupoid A. We can also think of F and F prime as zero cells in the identity type or the identity groupoid, because these types are sort of enriched in themselves. So for every two objects, X and X prime, we have a new groupoid, the groupoid of identities from X to X prime. So F and F prime are one cells in one and zero cells in another groupoid. And here alpha is sort of a two cell from F to F prime in A, or it's a one cell in the groupoid X of identities from X to X prime. There are many constructions available in univalent foundations on groupoids. In particular, we have the groupoid of functions or functors. So if A and B are types, then we have a type of functors from A to B. And importantly, we have a universe, which is a type of types, which I will discuss in just a second. Importantly, we can stratify the types in type theory according to how complicated the groupoid structure is. So if this is a groupoid, and at some point these identities may become trivial, and we call a groupoid a proposition when the identity is already trivial on this very first level. So when we have at most one object modulo identity in that groupoid, and we call a groupoid a set if the identity becomes trivial here, so if it's sort of a discrete groupoid. So what does Kowalski's univalence axiom say? First, before I come to the univalence axiom, I should discuss something that might seem obvious but is extremely important. Any construction that I can do in univalent foundations is invariant under identity. So everything is sort of a functor. That means if I have a type A, and objects x and y in A, and I have a construction on A, so this is the type theory way of talking about a construction on A. Think of it as a predicate on A if you want. If the identities from x to y give rise to equivalences of types between the constructions over x, between the fibers over x and the fibers over y. This is just a result of the inductive definition of this type of identities. And now, what the univalence axiom does, it gives a characterization of the identities between two types. That is, it gives a characterization of the groupoid of types. Namely, it says that the identities between types are the same as the equivalences between types. And the equivalences between types are just like equivalences between infinity groupoids, so it's functors back and forth that are suitably inverse to each other with some coherence condition. So, as a consequence, if I combine this equivalence with this thing here, I get this transport principle, which states that any construction on types that I can do in univalent foundations is invariant under equivalence of types. And this is sort of, if you want, this is a very simple univalence principle for mathematical structures that are just consisting of a type.
Sorry, yeah. I can't help but notice that this only goes in one direction. Do we expect this to be an equivalence, like if all constructions are sort of...
This one here?
Yeah.
Yes. It's at least a bi-implication. This type of equivalences might have a different homotopy. Type might be, this is a groupoid, and this is a groupoid. They might not have the same truncation level. They might be different as groupoids, but they're maps back and forth. Okay. It depends a bit on what you quantify over here. Okay, that was a brief introduction to univalent foundations. Now let's get back to categories. What are categories in univalent foundations? Well, there are at least two options. This is sort of the option. If you are married to set theory, then you might be inclined to give this definition. You say that a category is given by a set of objects, and by a set I mean here a discrete groupoid, and a family of sets of morphisms together with operations of identity and composition. There's another option, which turns out to be more useful, which is the following. It's what I call a univalent category. It's given by not a set, but a general type or space of objects, a general type, space or family of spaces of morphisms together with identity and composition. Except that it's actually not a general space here and here. I do have to impose some restrictions to make this whole thing well behaved. Namely, I do want the homomorphism types here, I want them to be a set. I want them to be sets or discrete spaces, because otherwise these things here would be data of property. Yeah? And furthermore, I want to impose a completeness condition, which The intuition is that we have here some spatial information between the objects of a category, and we have the categorical information between the objects of a category. And we want, in terms of isomorphisms, and we want those two to coincide. So we call this a completeness condition because it's very similar. It's actually a truncated version of a completeness condition of rest of Siegel spaces. Yeah. Okay. So these are the univalent categories. To summarize what we've just seen, we have both strict and univalent categories. The strict categories have an equality on objects because the objects form a set. And the sameness of strict categories is isomorphism categories. We have the univalent categories where the objects are given by one groupoid. I haven't explained why this is a consequence of what we've seen, but that's how it is. And the morphisms are given by discrete spaces. And these things do not come with an equality of objects. But the correct notion, or the notion of sameness for these categories is the notion of equivalence. And this is what we proved in 2013. Is this theorem, which says that the groupoid of categories has as its identity types, as its identities, the equivalences, the adjoint equivalences of categories. And as before, if we plug this equivalence into the general transport principle, then we obtain that any construction on univalent categories that we can express in univalent foundations is invariant under equivalence of categories. So in other words, univalent category theory is always automatically good. Now this condition, we'll go back. This condition looks very restrictive because it resembles the condition of a skeletal category, but it's not at all comparable to that simply because this is not equality. And so, whoops, sorry for that. So as a consequence, we do have a lot of univalent categories. For instance, the category of sets, of groups, and so on is univalent, and there are a lot of closure properties. So your constructions on univalent categories typically don't lead us out of univalent categories, but if they do lead us out of univalent categories, we also have a free completion operation to build univalent categories. Okay, that was my quick introduction to univalent categories. And now the goal is to generalize this to other mathematical structures. Yes. Are there any questions right now? No. Yeah.
You said that the category of sets and functions was univalent. Are there like classical categories that are not univalent?
The simplest example is maybe a category with two objects that are isomorphic but not equal. So that's
You gave this statement about units and associativity. Of course, these are things living in identity types, I assume.
Sorry, I'm not sure I can hear you.
Sorry, we have unitality and associativity, and
Yep.
these live in identity types.
Yep.
But I imagine that you have things like associators higher up, but you don't have to say this because it's discrete.
Yes. The discreteness means that it's automatically there are no higher coherences.
Yeah, and that's like a formal show that I don't see.
Yeah.
Okay,
Really, I need these guys here. Oops, sorry, I'm not used to the clicker. I'm looking very erratically. I need these things, these types. They are propositions in the sense that I mentioned earlier.
Right.
Okay. So their inhabitants are unique. Yeah.
I'm not into this. Only size issues.
I'm not talking about size. I'm pretending that we have one universe, but we actually have a lot of universes, and they are the usual size issues. But in addition to the size issues, the question of size, the question of dimension or of complexity of homotopy level. Yeah, I'm only talking about that.
Space of objects, space of arrows are same kind of spaces, same type of space. There is no size issue between the space of objects and space of arrows.
Well, formally, I have many of these universes U, so they are indexed kind of by a universe level, and I need to pick a universe level for the objects and for the morphisms. But I'm not talking about that because it's the same issues essentially as we have in set theory. So that's just Yes, of course.
Do you think it is mathematics or is it the project of future mathematics? Because something which will become mathematics one day.
It's absolutely mathematics. Yeah.
If it is mathematics, where are the
Can we possibly leave a question like this for the end rather than...
Okay.
There are still 4 minutes.
So, yeah, right. So, this is just a brief overview. We have a paper which will be published in the memoirs of the AMS. It has 180 pages or so. It's plenty of definitions and theories. Okay. So, the question now is how to generalize the Univalence principle from categories to other things. And in this paper that I just advertised, we developed a notion of signature for mathematical objects. A signature specifies the data of a mathematical object. And we have a notion of structure of the signature, and these are the models of the signature. We have a notion of equivalence of structures. All of these things are derived from the notion of signature mechanically. And we have a notion of univalence of structures, which is also derived from the signature. And then on top of signatures, we have a notion of axiom, which results, so a signature together with axioms on top of that signature yields the notion of theory. And theories have models, which are the mathematical objects we're interested in. And then we prove the following theorem. Given a theory T and univalent models M and N of T, then the equivalences, in this sense, the equivalence of structures between M and N coincide with the identities between M and N. And this means, as before, that any construction that we do on univalent models is invariant under this notion of equivalence of structures. As an example, of course, the theory of categories expressed in this way yields as the notion of equivalence the essentially subjective and fully flexible functors. And the univalent models of the theory are the univalent categories, or are equivalent to the univalent categories that I've just discussed. I want to stay with the example of categories, because this is really the example. Once one has understood this example, one understands the definitions. I think I jumped in a slide, yes. So, in our paper, we have two notions of signatures. We have what we call the diagram signatures and the functorial signatures. And here I'm showing diagram signatures. I'm not discussing the functorial signatures. They are more general, but also more complicated. A diagram signature is a picture like this, is essentially a one-way category where the objects specify the sorts and the arrows specify dependencies between sorts. So here, and this is the signature for the structure of categories. It has a sort of objects, a sort of arrows with two dependencies from arrows to objects, and then it has a sort for triangles, meaning for composable arrows, a sort for identities, and a sort for equalities between arrows. The signature of a strict category is more complicated because we additionally want to have an equality predicate on objects, so we add this second equality sort. Yeah. Of course, some of these composites of arrows should coincide because I want this identity to be a predicate only on endomorphism, so I asked that this arrow followed by the source is the same as this arrow followed by the target, for instance. Okay. Now, if we have this signature, what is a structure for that signature? Well, the structure consists of one type for the objects, then a family of types parameterized by pairs of objects corresponding to these two arrows here. So a family of types parameterized by pairs of objects, a family of types parameterized by endomorphisms, and a family of types parameterized by triangles of morphisms, and the same for equalities. And now, this in itself, this is not well controlled, and we need to impose some axioms on such a structure. And here's the list of axioms that we impose. It looks quite imposing. We have, first of all, we need to ensure that composition and identity are functions. These are axioms 1 and 2, and the categorical axioms, and we have the fact that E should behave like an equality, so it should be a congruence for INT. And we have these strange homotopical axioms that relate these sorts, or the interpretation of these sorts in a structure with the background theory, with the underlying type theory, and the univalent foundations. And the good news is, this looks kind of ad hoc, but the good news is that we can just define a univalence condition that will entail all these axioms 5 through 8. So I don't have time to discuss this univalence condition, but I'm very happy to talk to anyone in the break. These are the steps to defining the univalence condition. We first reformulate the type of isomorphisms in the category and obtain a kind of the type of indiscernibilities. And the clue about indiscernibilities as opposed to isomorphisms in the category is that the definition of indiscernibility only depends on the signature. Yeah? It does not depend on the fact that composition is a function, for instance. And also, this definition of indiscernibility, it transfers to other sorts in the same signature, but also transfers to all kinds of sorts in different signatures. Yeah? And that gives us a way of defining univalence for models or structures of any theory. And I don't have time to explain this. This is what it would have looked like. It looks a bit crazy, but yeah. And sorry, so I repeat this univalence principle. Then in the paper we have plenty of examples that we have discussed in great detail. So what are the univalent models? What is the notion of equivalence between these things? And in all these examples, the notion of equivalence turns out to be the right thing. For instance, for the dagger categories, the notion of equivalence is that of a unitary equivalence. So I think that's the right name. Where we discussed the unitary isomorphisms. So, one restriction that I want to mention is that we currently can only, our definitions can be stated for signatures of arbitrary height, of infinite height, but our theorems work by induction on the height of a signature. So we only have, our statements only hold for structures, for theories that have a finite height. Okay, thank you very much.
There is time for one quick remaining question.
Hi, thank you. So my question is, does working in univalent foundations help you with proving coherence for higher structures?
The question was whether working in univalent foundations helps with proving coherence for higher structures. Can you give an example?
Say I want to define, I don't know, monoidal structure in a bicategory. Does like working, say, in a theoretical foundation where I have univalence with univalent categories, help me just like specify that they can get coherence like automatically out of the correctness of the definition, or?
No, I don't think so. So, for instance, when you want to relate monoidal categories to strict monoidal categories, you want to strictify something. Actually, what it is a passage probably a passage from univalent categories to strict categories. Because in one case you want to discuss equality of objects, and in one you do not want to discuss equality of objects. Is that right?
That will have to do. I'm sorry, but we have to continue with the morning program. Thank you very much.